So let's look at another example of implementing a Metropolis-Hastings algorithm, and then we're also going to look at assessing essentially how well we've done with our Markov chain. Has it converged to its stationary distribution? Have we run the chain long enough, etc. So we're going to go back to the placenta previa birth example that was first introduced in chapter 2. And so the idea is that we're trying to estimate the true proportion of placenta previa births that are female using a sample from the European population. We're going to assume that our data distribution is binomial with 980 trials, and theta is the probability that a birth is female. We're going to assume that theta has a uniform 0-1 priority distribution, pretty standard priority distribution, and then our jump distribution for our Metropolis-Hastings algorithm is going to be an independence distribution. So it's going to be beta, alpha, beta, and you can see here that we get to choose the parameters alpha, beta, but it's not going to depend on a previously sampled value in our chain, which is what makes it an independence chain. So let's look at the R code that we're going to use to implement this. And so I'm going to write this function MH standing for Metropolis-Hastings algorithm. So it's going to take B, which is the total number of iterations I want my chain to produce. Start is the starting value for theta, so the first value I'm going to use in my chain. Jump.parm is going to be the two-dimensional vector alpha and beta that sets the parameters in my jump distribution. So once I have that, I need to store the values I'm going to sample for theta. So I'm going to create a numeric vector of length b plus 1. The first value is going to be my starting value. And then, starting at iteration 2 up to the length of theta, I need to iterate through my MCMC chain. So I'm going to draw a value theta star for my jumping distribution. So one value from that beta distribution with parameters alpha and beta. And now I need to compute or decide whether I'm going to accept that value sampled from my jump distribution. So I need to compute my acceptance ratio R. And if you remember, it's typically better to do that on the log scale. And so this is a sequence of complicated commands, and so I just want to look at that in a little bit more detail. So in general, the acceptance ratio R that we use in the Metropolis-Hastings algorithm is the Q function, the unnormalized density for theta star given Y. So this is the unnormalized version of our posterior distribution, divided by the density for our jump distribution. We evaluate it at theta star given the parameter value theta t minus 1, the value from the previous iteration. And then we divide that by the unnormalized posterior density evaluated at theta t minus 1. And there's actually should be a divided here. Divided by the jump density evaluated at theta t minus 1, assuming the parameter values are in some way dependent on theta star, which is the value sampled in the current iteration. And if you remember, Q theta star given Y, or unnormalized posterior density, is the likelihood function multiplied by the prior density. And so now we want to look at what that is on the log scale. And so what I'm going to get here, so the log of R is going to be the log of the likelihood function evaluated at theta star plus the log of the prior density evaluated at theta star minus the log of the jump density evaluated at theta star given theta t minus 1. So that's just this numerator part right here. And all of that, so we're going to take that quantity and then we're going to subtract from that the log of everything in the denominator here, which is going to be the natural log of the likelihood function evaluated at theta t minus 1 plus the log of the prior density evaluated at theta t minus 1 minus the log of the jump density evaluated at theta t minus 1 given the currently sampled value theta star. Okay, so this really just has to do with the properties of the log function applied to products and to quotients and simplifying. And so we're going to use this, essentially this formula right here, when we evaluate our algorithm below. And because this is a little bit complicated, I want to break it up into the numerator part and the denominator part. And so you can say I have the numerator here, So I have the log of the data density, or data distribution, so it's a binomial distribution. I had 437 successes, that's my observed Y. The number of trials was 980, and my parameter value was the current parameter value theta star. I add to that the log of the beta density, because beta was my prior distribution. I'm going to evaluate that at theta star, and the parameters of the prior distribution were 1, 1. And I'm going to subtract from that the subtract from that the log of the jump density, which in this case is also a beta distribution. I evaluated at theta star, and because this is an independent chain, it actually does not depend on theta I minus 1 in any way. So I just need to plug in alpha and beta. I do something similar for the denominator part of the R, the acceptance ratio R, except that everywhere previously I had a theta star, I now have theta I minus 1. And then I need to take the num.r and I subtract from that den.r, the denominator part. And that gives me really log r, so I should have called this log r in my code to be a little bit more specific. And now I need to decide based on that acceptance ratio whether I should accept the currently sampled value. So I take a value from a uniform 0-1 distribution, I take the log of that value, and I'm going to accept it as long as that sampled value is less than or equal to the minimum of r and 0. And if I accept it, then my current value of theta is set to be the value I sampled, theta star. Otherwise, I'm going to keep the previously sampled value, theta I minus 1. So that's my function that I use to implement my independence chain. And I'm going to set my seed so we can get the same results. And so I want to construct chains of length 10,000, not including the original starting value. I want to keep the second half, so I'm going to discard the first half as burn-in. And I'm going to set the parameter values of my jumping distribution to be 1, 1. And so I'm actually going to, my jump distribution is actually going to be the prior distribution. And you can see I have a number of different starting values here, 0.01, 0.25, 0.5, 0.75, and 0.9. I wanted to use 0.99, but I was actually running into numerical problems, so the chain wouldn't run. But these are still pretty over-dispersed. It should give us a good idea of whether our chains have converged to the stationary distribution. So I run that first chain, and then after I do that, then it'll start running to the second chain. Now that I have sampled values for my 5 chains, I should determine whether I have in fact converged to the stationary distribution in my chains. So I'm going to load the CODA package so I can implement some of these diagnostics. And essentially what we have to do right here is we have to get the data in the proper format. So many of the diagnostics are going to be applied to an MCMC list. And so what I do here is I take the values I want to keep in my chain, I convert them to an MCMC object. If I stack a bunch of them together in the MCMC.list function, it's going to create an MCMC.list object with 5 chains. And so I'm going to create that chain. And if I run the trace plot function on that MCMC.list object, it's going to give me a trace plot for each of my variables. In this case, I only have 1. So I run the trace plot function there, and here's what we see. And you have to remember, I've already discarded the warm-up here, so we don't have any unusual starting values. And it's a little difficult to see because we have so many different iterations in our chain. But it appears that there's a decent amount of movement here, and it seems like they're sort of staying in the same area. So it looks promising to me that, in fact, these have converged to the stationary distribution. Now we'll look at an autocorrelation plot of our MCMC chains. And this function actually produces an autocorrelation plot for every single chain, just in case there's one chain that has particularly bad starting values or is particularly correlated. So there's a first one. You can see that they're correlated out to maybe even 35 observations, or a lag of 35, though we definitely see some exponential decay. So this is not ideal, but it's better than if we saw an autocorrelation plot where there's really no decay at all. So that was the AC F plot for the first chain. For the second chain looks similar. The third chain looks similar. Fourth chain and fifth chain. And so they all look pretty similar. There's definitely some autocorrelation in our chain, but we're seeing some decay over time, which is good. Now let's look at our effective sample size for our MCMC chain, or MCMC chains. So combining the information from all of the chains, and you have to remember, so we sampled, so B was equal to 10,000, and we threw away half of those. So we actually have 20,000 sampled values that we've kept in our MCMC chain, and the effective sample size is only about 1,500 observations. So this is not particularly encouraging in my opinion. So we still have 1,500 an effective sample size of 1,500 for our MCMC chain, but we'd really like to see this to be a much higher number. So this makes me think that perhaps we actually need to run our chains for longer in order to better estimate the target distribution. So now we can actually look at a plot of the Gelman-Rubin diagnostic. And so this is not going to give me, oh sorry, this is going to be the Gelman-Rubin statistic. So I'm going to run this command here. And if you remember, I need multiple chains to get this. And so the point estimate is 1. Okay, so that's good. So we remember if we wanted r hat close to 1. And the upper bound for that is 1.01. And so it seems like, according to the Gelman-Rubin diagnostic, that essentially our chains have converged to the same stationary distribution. And you can actually look at a plot of the Gelman-Rubin statistic as a function of iteration, which we'll do now. And so it's computing that within variance, and comparing that to the between variance in the different MCMC chains, and then it's going to plot that as a function of iteration number. And you can see that at the starting value, it's pretty high at the beginning, but then it's converging toward 1. And so after about 2,000 iterations in our chains, it looks like we're converging roughly to the stationary distribution. So that's also another promising sign that our MC algorithm has converged to the stationary distribution. So now let's look at the results of the Heidelberger and Welch test for our binomial parameter theta. And so we have 5 chains, and so we're going to have tests for each one of those chains. And we can see that the stationarity test passed for the first chain, though it actually doesn't look like by very much. But we can keep the entire chain. So it says start iteration is 1, and so we can keep the entire chain. At least this particular diagnostic says that the chain has converged to its stationary distribution. And now we perform the half-width test. The half-width, or margin of error for our confidence interval for the mean, the posterior mean, is 0.002. The estimated mean is 0.447. When we take the ratio of the half-width to the estimated mean, we get a very small number. And consequently, that's going to be less than epsilon. And so we pass the half-width test as well. We can estimate our posterior mean with a pretty high level of accuracy. And we see similar results for all the other chains. And so at least based on this diagnostic, this gives us confidence that our chain has converged to its stationary distribution and that we are estimating the posterior mean with a relatively high level of accuracy. So the Raftery diagnostic, so let's run that one real quick. You have to remember this is looking at how many sampled values we need to estimate a quantile with some level of accuracy with the desired probability. And it's saying we don't need to discard too many values in our chain, which is good since we've already discarded about half of them. But it says to achieve this level of precision, we actually need something like 58,000, close to 59,000 values in our sample. We have roughly 20,000 that we actually kept after discarding actually I guess we have 5 chains, so I guess we actually have 25,000. But basically what this is saying is that the dependence factor, because it's very high, it's much more than 5, we actually need a longer chain if we want to estimate quantiles for these upper tail quantiles or lower tail quantiles from our target distribution. So at least according to this diagnostic, it would actually say we need to run our chain for longer. Lastly, we'll look at the Gwicky diagnostic. So basically what it's doing is it's comparing the mean in the first 10% of our chain to the last 50% of our chain, and it's going to do this test for each chain. And we see that our z-scores here are between -2 and +2. So at least in terms of estimating the mean, the Gwicky diagnostic would say that we have in fact converged to our stationary distribution. So most of these diagnostics are encouraging. There's one that says that if we want to estimate some of these upper quantiles, lower quantiles, that we may need to run our chains for longer, but there's no clear indications of major problems. However, if we change our jump distribution somewhat, we can in fact get different results. And so I'm going to run the same, essentially what I'm going to do is I'm going to run the same algorithm. I'm going to create 5 new chains, but instead of using a 1, 1, 1, 1, 1, and 1 for the parameters in our jump distribution, we're going to use 3, 3. So it's going to be a different beta distribution for our jump distribution. And these chains are going to have to run a little bit longer because, as you can see up here, we're actually not going to keep the second half. We're actually going to keep every 10th observation in the second half of our chain. So we actually have to run our chains for much, much longer in order to get the desired number of iterations. So now that we have obtained the values from our 5 chains, we're going to once again construct an MCMC.list by taking the values in each chain, subsetting the values we want to keep, converting those to an MCMC object, and stacking them all together in one object, which we're going to call MC. We can now construct a trace plot of our MCMC chains. I expect it to look somewhat similar to what we saw before. And so we see here that all the chains are pretty much overlapping. We have a decent amount of movement. I think so, at least. It's hard to see on this scale, but at least this plot of this trace plot seems to look okay. If we look at the autocorrelation plots for each of the chains, we see that there's much less autocorrelation than before, and that is good news, but really the only reason that they're looking better is because we only sampled every 10th value in our chain. You can look at our effective sample size. So we see 14,000 values in our chain, which is good news. We actually kept 25,000 of the values from our 5 different chains, so 25,000 total, so that's quite a bit better than what we saw before. But once again, our chains actually had to run for much longer because we only kept every 10th iteration. If you look at the Gellman-Rubin statistic, it looks very good. So our estimate of R hat is 1. The upper bound also reduces down to 1, so that's a good indication that our chains have converged to the stationary distribution. A plot of the Gellman-Rubin statistic versus iteration is also going to look good, I'm sure. So we see that after about 10,000 iterations in our chain, we're converging down here to R hat of 1, so that's good news. If we look at the results from our Heidelberg and Welch diagnostic, we once again see that we're passing the half-width test, so that's good news. The Raftery diagnostic, let's see what that says. So we can see that our dependence factors are much, much lower, which is excellent. And because the dependence factors are much lower, the total number of values in our sample that we need to achieve this level of accuracy is much lower than it was before. And it's saying that this level of precision, it can be achieved after about 5,600, so 5,900 here, so maybe somewhere around 6,000 iterations or 6,000 values in our chains. And since we have 25,000 in our chain, that's good news. We've definitely passed the Raftery diagnostic as well. And if we look at our Gwicky diagnostic, we see that we're getting small z values, except for this one actually, surprisingly. So this one doesn't look quite as good. But considering how many tests we've done and considering how good the diagnostics are looking, there's really no indication that we have problems with our MCMC algorithm. It appears that our chains have converged to their stationary distribution, and so from this we could go about looking at the posterior distribution of our chain and computing other quantities of interest. Now we can look at the results of the Heidelberger and Welch test for the second MCMC sampler that we implemented. So we once again start by looking at the result of the stationarity test, and the test passed with flying colors. We have a huge p-value here, and it says the start iteration is 1. So we passed the stationary test for the entire second half of our MCMC chain. So that's good news. And then we also look at the results for our half-width test. So the half-width or margin of error for our confidence interval is 0.0006, so a very small number. Our estimated mean is about 0.45. When I take the ratio of the half-width to the estimated mean, I get a very small number, will be much less than epsilon. So we also pass the half-width test. And I see similar results overall for the other MCMC chains. And so just like in the first MCMC sampler, the second sampler, based on the results of the Heidelberger and Welch test, says that the chains have converged to their stationary distribution, and that we have run the chains long enough to get a relatively precise estimate of the posterior mean.